Time for DCL 603. This will be my third in my series on grounding in ham radio. As promised, I'm going to talk about grounding for lightning protection. I'm also going to talk about EMPs in this presentation. This video, like all of my videos, are directed to those of you who are new to ham radio or new to radio in general. I try to bridge the gap between what you studied to get your license and the more advanced material that you would learn in a college physics course. We don't have to go that far, but there are some concepts that I don't think are fully covered in the license manuals, and I'd like to present them, along with some practical knowledge that would help you on your ham radio journey. First of all, I don't think anyone's asking why. We all know why we want to protect from lightning. We don't want our stuff damaged. What are we really trying to do? Well, we want to prevent strikes when we can, and if a strike occurs, we want to prevent damage. The only problem is we can't prevent strikes. Lightning is going to strike. So let's just concentrate on preventing damage. How? I have an easy way. I've been a ham operator for 50 years. I disconnect from the power line, and I disconnect my antenna lines and throw them out into the yard before the storm hits. I've done this my whole life. I realize many hams don't want to do this, or they want to stay on the air, or maybe they go to work and forget to disconnect. In those cases, we've got to do a little more than what I do. The primary mission here, we've got to provide a path for lightning current to ground. I don't mean to our ground system. I mean, let's get the current into the ground. We want to make the current flow the way we want it to. We don't want it flowing through our equipment. We know it's got to flow. We don't want it to flow through our equipment. A big part of this entire challenge is to minimize inductance and resistance in the grounding system. If you're not familiar with inductance, don't worry about it. If you're not familiar with the resistance, you really should study Ohm's law and understand that resistance is anything that resists the flow of current. I'm assuming if you're a licensed ham, you've already covered that. Now there's two kinds of strikes. Obviously the direct hit. Lightning has hit our antenna or our tower, or it's hit the power line feeding our shack. The near miss or the indirect hit is a bit of a challenge. This is where lightning hits the tree in your neighbor's yard, and that's not exactly a lightning hit to you. However, anytime there is a current flow, a field is produced. Lightning is a current flow. Now, that field will inductively couple energy into any nearby conductor. Your antenna wires, coax, everything is a conductor. What works for direct hits generally works for the near miss, but not completely. What works for a near miss are things like DC grounded antennas and direct ground rods, things like that. The problem is if you are coming through a lightning arrestor, many lightning arrestors don't fire or don't protect well unless the voltage and current coming in are very high. So there can be a little bit of a challenge to the near miss or the indirect hit. So let's get started. This is a redoing of my video from before. Notice I've removed everything from inside the house, and all I have is the breaker panel in the house and the grounding system outside of the house. Notice the two power wires coming into the home are not shown. This is because, for the most part, we're concerned with ground currents. Yes, a surge can come in on the power line, but normally what happens is lightning hits out here, there's a conduction here, there's a lot of current, and there's a surge that comes down this wire. Yes, it can couple to these two as well, but the majority of the current and the potential is in the ground wire. These will elevate to the same voltage as the ground system, but there's no reason for an arc usually between the two because the voltage is equal. Now, how things start off is the top of the cloud gains a positive charge, the bottom of it gains negative. This makes the ground seem positive. So what's going to happen is there's going to be a discharge between plus and minus, or minus and plus, depends on how you want to look at it. Lightning is not trying to strike your equipment. Lightning strikes between the cloud and the ground. It's you, or your tower, or your power line that got in the way. The reason I make a big deal out of this is just think of it this way. Think of it as a discharge coming out of the sky. It isn't really necessarily, but just think of it that way. It wants to get to ground. If it hits here, it doesn't want to come into your house and destroy stuff. It wants to go to ground. It'll also partly go to ground this way. Just think of it that way. Ground is the destination. You don't want to be in the way. Now, let's talk about the power line. The reason I want to talk so much about it is in my 50 years as a ham, I've never lost any equipment to a lightning strike to one of my antennas, mostly because my antennas are always disconnected. But I have lost equipment and home appliances to power line surges. All right, now I've kind of cleaned things up a little bit here, as I said before. One thing I did, though, is I added a spark gap. The spark gap is fundamental to lightning protection and keeping your power on at home. Let's take a really close look at it. The spark gap fires when voltage across the spark gap gets high enough. Now, in a normal atmosphere, when you get to 3 million volts, you can jump 1 meter. That means if you get to 3,000 volts, you can jump 1 millimeter. They design these gaps to fire at the voltage they want them to fire, but not lower. Now there's a really cool thing that happens here. When the spark gap fires, some protective equipment at the electrical substation goes into action. Now, once this arc occurs off lightning, lightning is going to hit, let's say it hits the power line. The voltage gets very high between here and ground. This arcs. When the arc happens, the spark gap looks like a dead short. So the lightning surge goes to ground. But the power line is shorted. This causes current coming out of the substation to go very, very high. When it does, the circuit breaker at the substation opens and shuts power off. Except for one thing, there isn't a circuit breaker at the substation. There is a recloser. A recloser is a circuit breaker that opens, waits a certain amount of time, then it recloses. If the fault is gone, it just goes on with normal operation. If the fault is still there, it opens and closes about 3 times. If the fault doesn't go away, like a tree limb is shorting the line, it locks itself out and waits for a lineman to come along and fix the issue. But if lightning hits, the recloser will open because of the high current, wait a few seconds or less, reclose, the power comes back on, and everything's fine. This is why during an electrical storm, a lot of times the lights will go out and come right back on. That was a spark gap firing due to lightning, usually lightning, the recloser opening and then reclosing. When your power flickers like 2 or 3 times and goes out and stays out, that's because there was a permanent fault, like a short somewhere on the line, and the recloser finally said, okay, I tried 3 times, I'm done. Now, here's what we want to happen in a lightning strike. Lightning hits, in this case, apparently as the form of a big red arrow that comes out of the sky. When it hits, The voltage in the power line, that is the black lead, the hot lead, goes very, very high. The ground stays at low voltage. The voltage level of the spark gap is exceeded and it fires, shorting the line. What we want to happen next is this. We want the lightning current to go to ground. Well, it does, but it doesn't do it like this. The lightning current heads for ground like this. It divides based on the impedances, or that is the inductance and resistance of each lead. Path 1 is going to take most of the current in almost every case because the ground there is a ground wire that is straight and it goes right to the stake or to the ground rod. At the house, well, that path is curvy and twisted. There's a little more inductance. There might be some more resistance. Maybe our grounding system at the house hasn't been maintained properly. So it's hard to say how the current is going to split, but it's going to split. Now, think about something. Let's say you had 1,000 amps flowing through path 2. 1,000 amps. Remember Ohm's law. Amps times resistance equals voltage. If there's 1 ohm of resistance between the breaker panel and the ground, and you have 1,000 amps, the breaker panel now shoots to 1,000 volts above ground. In fact, everything in the house tied to the breaker panel shoots to 1,000 volts above ground. Frankly, if everything goes to 1,000 volts together, we're all like a bird on a wire. We're going to be okay. But if you're in contact with an electric device that goes to 1,000 volts above ground, and you happen to be in contact with a water pipe that is well grounded, you have 1,000 volts across your body right now. For that reason, A, you want to stay away from stuff during an electrical storm. B, you want to make sure the circuit from the breaker panel to the ground rod is in good shape. I am a firm believer in welding ground wires to ground rods for this very reason. So let's add the shack. My first ham shack was a 19-foot mast. Well, maybe it was a 15-foot mast, aluminum. And I had a little 2-meter ground plane here and my radio. I didn't ground the mast because a 19-foot tall antenna wasn't even as tall as the house. Yes, an induced charge from a near miss, a lightning strike 1,000 feet away, is going to generate a bit of an electrical surge through this metallic material here, the cable, the antenna, the mast. But it's probably not going to be enough to be too much of a concern, so I never grounded it. Well, then what happens when lightning hits? This is a graph of the current. Now, the voltage at this point, again, is a function of the current times the resistance here. So this might go to 1,000 volts instantaneously and then go back down. If the mast is not grounded, no current's actually going to flow. It'll go high in voltage and it'll come back down. Nothing bad will happen. But let's ground the antenna anyway to make things better. So, all right, now look, I did a really good job. I CAD welded this. This is welded. So this is a good ground, I guarantee it. Lightning hits and my radio gets blown up because I grounded the mast and because there was a little resistance here. So I had 3,000 or 4,000 volts here for an instant. This ground was newer and I welded it. It's in better shape. So the current, although the current tried to flow this way, it saw a lower resistance path here, or somewhat low. So several amps or tens of amps of current flowed, destroying my equipment. So by grounding my equipment, I made things worse. So lesson number 1, we should never ground our masts or our towers, right? Well, of course, that's wrong. It's just that we've got to do it intelligently. So let's move on and put in a real tower. No one is going to erect this tower, including me, without doing some serious grounding. You know it's going to get hit. So I put multiple rods in, I welded everything together, I did the best job I could do. The problem is, as before, I have created a possible disaster. Because if lightning hits this, a lot of the current will go here. Some of it is going to go through here to this ground and out to the street. Or if lightning hits here, some of it's going to come down through here. Most of it will go this way. Some's going to try to go this way. So obviously I've made a big mistake. How do I fix my mistake? I go to the store and I get some 3 or 4 inch wide copper strip, or at least some like number 0 cable. I prefer copper strip for something like this. I'm going to weld here, I'm going to weld here, I'm going to weld here. Now, I'm going to talk more about it later, but because I used copper strip, there's very little inductance and very little resistance here. This being number 12 wire is inductive and it's somewhat resistive to lightning or any higher frequency effect electricity. So most of my current's going to go right down through here, distribute between the 3 ground rods, everything's going to be fine. Is everything really going to be fine? Well, no, because there's still a potential path through the radio. And now I have a lightning rod in the form of a tower to make sure that I take damage. So I do this. I have put in a grounding panel and I bonded it with a copper strip to the ground system. I've then added 2 lightning protectors, one for the coax, one for the power line, and I've run my power through that. Now what I've done, let's consider current coming down through here. Most of it is going to want to go in here and travel into the ground system. If a little bit of it wants to go this way, that's okay. It won't be much. But there's no such thing as current going in a circle. The radio is completely protected now. Now we've done it right. And again, if you can't afford copper strip, use a couple of pieces of number 0 wire and just make sure you weld at every connection. This is how I do grounding. This is also how we do grounding in commercial radio. Many call this the single point ground system or a single point ground installation. I have talked a lot about inductance. Let's wrap up inductance so that you really understand what I mean. We'll talk a little bit about the safety ground, how it relates to lightning, and let's not forget EMPs. So is that 3rd wire in the electrical outlet a ground or not? Well, it's a safety ground. In other words, 60 cycle current can use this as a very effective ground. For lightning, no, it's not something you want to rely on. The reason is this: inductance. Inductance is a weird behavior of a piece of wire or a coil that resists any change in the amount of current flowing through it. That means if you try to send current through it, like in a lightning strike, it tries to stop the current from flowing. Now, once the current starts flowing, it also tries to keep it flowing, but that's not our point. The point is, it tries to keep any change of current from happening, and if you're at 0 amps, it tries to keep you at 0 amps. To take it a step farther, if you take into consideration the inductance of the wire and the frequency of the current, you have what is called inductive reactance. In fact, you can multiply inductance times frequency to get the reactance. Notice that with DC, the frequency is 0, so there is no reactance. So inductance doesn't matter at DC. Why doesn't it matter at 60 cycles? It doesn't matter at 60 cycles because 60 is such a low number here. I know it sounds high, but it's not. that it doesn't matter. So at 60 cycles, there's not enough inductive reactance in that number 12 wire to matter. Lightning has an effective frequency of millions of megahertz. So lightning tends to have an effective F in the millions. That's why that piece of wire is not a lightning ground. If you want to learn more about inductance, look up these two videos. Now, before I go farther, let's get into inductance just a little bit, and I'll show you how it works. Or at least I'll show you partly how it works. All right, we have a black wire. A current is flowing to the right. As the current gets stronger and stronger, magnetic lines of force come out from the wire and form loops. When they come out from the wire, as a result of current, they cut through that green wire. When they cut through the green wire, it produces a voltage in the opposite direction, which also produces current. When the current in the black wire stops, the magnetic field collapses back on the black wire. This causes the current in the green wire to reverse direction, oddly enough. All right? So we have a counter EMF being generated in the second wire by the magnetic field that was caused by the current in the black wire. What if I took the black wire itself and wrapped it into a coil? Now my magnetic field lines that are a result of my own current are cutting into my own black wire. So now the counter EMF being generated is generated and acts within the wire that generated it. So this counter EMF in the black wire is what we call inductance. It tries to stop the current from flowing, or if it's already flowing, it tries to stop it from changing how much it's flowing. Again, we're most concerned with the fact that we start out with no current, lightning hits, and current tries to flow. Inductance tries to stop it. Now, amazingly, this actually happens on a tiny scale, even when the wire is straight, because these magnetic lines of force come out from the inside of the wire. They set up what is called a skin effect. This means if you've got AC flowing through the conductor, the AC current will tend to flow only on the outside of the conductor. This means we have less material or diameter for current to flow. It only flows on the outside, so you have more resistance, so you have less current. So the skin effect and the inductive kick from the wire both combine to make high frequency AC not want to flow through the wire. Now, 60 cycle current, it's not that big of a deal. It's not a big deal, okay? But high frequency current is a big deal. Copper strips have a lot more skin area than a number 14 or number 12 wire, which is why I keep pushing you toward a copper strip. Now, if you got a number 0 wire, that would be better than number 14, of course. A number 0 wire is really big. The best thing, though, would be a copper strip. Now, let's look at something else. I keep telling you, I think I've told you, lightning is considered DC, but it has an AC effect to it. That AC effect is called, or is caused, by the rise time. Now, let's look at rise time. Here we've got our 60 cycle AC current. And because you get 60 cycles in a second, that means 1/60th of a second goes by every time you have a cycle. Well, you can do some really, really easy math. 1 divided by the frequency in hertz tells you how many seconds it takes for a cycle. In this case, it's 0.0167 seconds. That seems like a short time. In the electronic world, that's a long time. That's not a big deal. What's rise time? Now, take a look here. How much time do you suppose there is between here and here as this voltage increases. See, as the voltage and current increase, that magnetic field come out from the wire. If you had twice the voltage and twice the current, the magnetic field would be twice as strong. It would fight, the counter EMF would fight the current twice as much. But because you already have twice the voltage to begin with, it all balances out. And it doesn't matter how much voltage you put in there. The action of the wire is going to be the same. The counter EMF generated is kind of going to even out with the current that caused it. But this rise time here, how long is this rise time? Well, if the cycle is 16.7 milliseconds long, the rise time is 1/4 of the cycle, isn't it? Because this is a cycle. Here's a quarter, another quarter, another quarter, another quarter. Okay, so rise time is 1/4 of a cycle, or 1/4 of the period. So you figure out the period of the cycle, and then you multiply that times a quarter. So now we know that this amount of time is 0.004167 seconds, or just over 4 milliseconds. That's still actually pretty slow. So it takes 4 milliseconds for these magnetic lines to form and for that counter EMF to be put back into the wire. All right, fine. By the way, there's another piece of math. You could also say 1/60th of a second. Well, 1/60th? 1/4 of 1/60th would be 1/240th. That math, 1 divided by 240, gives you the same number as you got down here, except I rounded it. All right, so we now know that rise time is important, that as the current rises, the magnetic field forms. The magnetic field causes a counter EMF that fights the current. Okay, fine. What happens if I do this? My rise time used to go all the way to here. Now it's like bonk. Right now, it happens really quick. That means the amount of energy that I put into it over this amount of time, I'm now putting all that energy into the counter EMF very, very quickly. So the counter EMF has a tremendously stronger effect. That means as I reduce the rise time, that is, increase the frequency, my counter EMF is way more powerful. This is why I say the higher in frequency you go, the more counter EMF, the more inductive reactance, and the less current. Well, I also said that lightning is DC, so what do we care about all this AC crap? Well, lightning is a DC pulse, like I showed here. It rises and falls. It's technically DC, but it rises so fast. If you blow up the image, the rise time of lightning is actually very short. That has an AC effect because your rise time is so darn quick that you throw the energy back into the wire and create the EMF incredibly fast. Remember I said 60 hertz, my rise time is 4 milliseconds. What do you suppose the rise time of lightning is? Well, it ain't much. 1 microsecond. At the end of the video, I will tell you where I got this number. But generally, all the sources say 1 to 5 microseconds seems to be a good value. That's hundreds of times faster than 60 hertz. Hundreds of times faster. That means a wire with a little inductance that works at 60 hertz isn't going to pass lightning very well at all. It'll pass it, but not very well. What about EMPs? How quickly do you suppose they form? When an EMP goes off in the sky, it sends the magnetic or the electromagnetic pulse through the air. That pulse generates a spike in voltage and current in your antenna and in your power line. What do you suppose the rise time of that pulse is? Well, how's this grab you? Yeah, it really is that bad. The EMP is way worse to filter than lightning. And again, at the end of the video, I'm going to give you a reference where I got that number. Do you see how difficult protecting from an EMP is compared to lightning? The only saving grace is the intensity of the EMP pulse is not going to be 10,000 amps that your lightning strike is, but it's still going to be considerable. Now, while we're on the topic, and before we move to the next video, I'm going to give you a little sneak peek. What do you suppose the rise time is in an RF signal in our ham bands? And again, we'll talk about this a lot more the next time. Here's a little teaser. By the time you get to 2 meters, the rise time is worse than an EMP. It's really that bad. Even on 20 meters, it's in the EMP range. What this means is, if you can learn how to effectively ground, not for lightning, but for EMPs, you can also ground for RF. Maybe I should put that backwards. If you can learn to effectively ground for RF, radio frequency, you've inherently created a ground that is the most effective with an EMP. And again, we'll talk about this a lot more in the next video. For now, just remember, if you want to play around, the period of a cycle is 1 divided by the frequency in hertz, not megahertz, hertz. Once you figure the period, multiply that times 0.25. Now you have your rise time, and you can look at the values for AC current, AM broadcast, 80 meters, the 5 gig band, anything you want. The numbers are very, very impressive. Just remember, 1 microsecond for lightning, 5 nanoseconds for an EMP, which is 0.005 microseconds. That's it for this time. Now, I made some promises in the beginning of the video, so let's get to that. If you want to really learn everything under the sun about grounding, well, maybe not everything, but a whole lot, go to w8ji.com and click on the ground systems link. That takes you to a page with, I think it's like 14 links. You can spend days reading Tom's material. Tom is the gentleman that designed the MFJ antenna analyzer. He designed, I think, all of the Ameritron amplifiers, most of the MFJ tuners, anything RF related that MFJ or Ameritron made, Tom had a hand in designing. Okay, one last item. Number 1, if power line reclosers were interesting, I don't expect you to type all this out. Go to Google, type in power line reclosers. Look for the first Eaton link. It'll be this one. It will take you to their article, Fundamentals of Reclosers. It's actually more an advertisement than anything, but there really is a lot of cool information on that page. Rise time of lightning. Where did I get that? I got it from all these guys that in 2012 wrote a statistical analysis of the rise time of lightning current pulses in negative upward flashes measured at Santa's Tower, published by the IEEE. You can find this on the internet. Another item is, remember I talked about EMPs. Well, one of the authors up here teamed up with this guy, and they wrote Transactions on Electromagnetic Compatibility. Pages 484 through 491 were derived and taken out and are now known as rise time in HEMP, high altitude EMP, E waveforms. They are both IEEE papers. You can find that on the internet if you want to look at how I came up with a rise time that I came up with. One last item, Roger Block with Polyphaser Corporation wrote, well, this is the second edition of the Grounds for Lightning and EMP Protection. That's actually a good publication if you can find it. It kind of goes over a lot of the grounding single point stuff I talked about. I don't know if you can still buy that anywhere on eBay or on the internet. In any event, I hope this has been helpful. I hope it was enjoyable and educational. Leave a comment if you've got any questions or comments. Look for the next video on RF and EMP grounding, probably by mid-April of 2025. Thanks a bunch, and I'll see you next time.